Two remarks. First, in the mainline videos, we proved the following. We proved that if p is a real polynomial, and if zeta is some complex number, then p of zeta is equal to 0 if and only if p of sigma zeta is equal to 0. So zeta is a root of p if and only if its complex conjugate is a root of p. That's what we proved in the mainline videos. And the first remark is that that same proof actually establishes a somewhat stronger claim. So the same proof that we gave in the mainline video, the same proof shows that for any p that's a real polynomial again, and for every zeta that's a complex number, what we have is that p of sigma zeta is equal to sigma p of zeta. So in other words, sigma commutes with any real polynomial p. And it's a nice thing to know this slightly more general version. Okay, so that was the first remark. Now the second remark is just a slightly different way of thinking about the fact that zeta is a 0 of p if and only if its complex conjugate is. So this is just going to be a different way, slightly different way, to think about the statement p of zeta is equal to 0 if and only if p of sigma zeta is equal to 0. And the way we'll get this slightly different perspective is to factor the polynomial p. Okay, so let's write p of x is equal to c0 plus c1 x plus plus cn xn. Now by the fundamental theorem of algebra, we know that p has roots in the complex numbers. So we can factor p. We can factor p into linear factors. So we can write this as, say, cn. I'm just going to pull the cn out here because it's kind of annoying. Cn times x minus some root lambda 1, then x minus some root lambda 2, x minus some root lambda n. So we can factor the polynomial p like that. Okay, so now what does this fact tell us? What does the fact that p of zeta is 0 if and only if p of sigma zeta is equal to 0 say? Well, let's write down the two things. So in the factored version, p of zeta is equal to cn times zeta minus lambda 1, zeta minus lambda 2, zeta minus lambda n, and p of sigma zeta is equal to cn times sigma zeta minus lambda 1, then sigma zeta minus lambda 2, sigma zeta minus lambda n. Okay, and we know that this guy is 0 if and only if this guy is 0. If the other is. One is 0 if and only if the other is. Okay, but let's think about it. When is this product going to be 0? I mean, if p of zeta is 0, that means that this product is 0. I guess we're discounting the case where cn is equal to 0 just by convention, because we wouldn't have written cn if cn were equal to 0 up here when we wrote down the polynomial p. So if p of zeta is equal to 0, then something in this product must be equal to 0, right? If this whole product is equal to 0, then one of the terms in this product must be equal to 0. So that's just saying that zeta is equal to lambda I for some I. That's all this first thing is saying. So the fact that p of zeta is equal to 0 just tells us that zeta is equal to lambda I for one of the I. Okay, but we know that P of zeta is 0 if and only if P of sigma zeta is equal to 0. So that means that this product is 0 too. And that tells us that sigma zeta must also be equal to lambda j for some j, say. So sigma zeta is also one of these lambdas. So both zeta and sigma zeta have to be one of these lambdas. They might not be the same one, right? Zeta might be lambda 1 and sigma zeta might be lambda 15 or something like that. But they both have to appear as lambdas. And so what that tells us, and this is where this gets interesting, is that sigma must be permuting the roots of P. So sigma, what it must be when we write out this factorization and we write out this factorization, is that sigma is just permuting the roots. It's taking each lambda I to a different lambda I. It's permuting the set of lambda I. So that's so important, let me write it down. Sigma must be permuting the lambda I, the set of the lambda I. And that's a perspective which is worth having too. All right, so those are the two remarks I wanted to make.